started looking at more than one single mode, that is multimode states, and we started looking at two more states and took some examples. Do you have any questions? Yeah.
Sir, we expressed the general get psi phi as a product of two n1 and n2. There was a general get which is summation over n1 and n2, cn1, n2 and n1 and n2.
Actually, for example, when we quantize electromagnetic radiation, I find a discrete set of infinite number of oscillators. Each oscillator can have energy of n plus half h cross omega. Each oscillator is characterized by its annihilation creation operators. Each oscillator is decided by its Ket state, etc., etc. So the complete state is given by, actually, if I have n1 photons in mode 1, n2 photons in mode 2, n3 photons in mode 3, nl photons in mode L, infinite. Okay, this is one set, one ket, for example, where there is one state in which there are n1 photons in mode 1, n2 photons in mode 2, etc. And this I write as n1, n2, nl. So this product means it is essentially this is a simplified form of writing the state.
No, this is fine.
Okay.
What I am asking is, if we consider two mode states.
Yes.
A general two mode state will be summation over n1, n2, c, n1, n2, and this.
Yeah. So I have, for example, I have c, n1, n2, n1 going from 0 to infinity,
Yeah.
and n2 going from 0 to infinity.
Now, under what conditions can we separate it into a form of a product of over summation of n1, summation over state n1 and etc.
It depends on this expansion coefficients here. If you had, for example, I would imagine that if this could be written as a product of a constant which is n1 and n2, then I can split this into two product of two sums. Means I can write this as sigma n1 c n1 n1 sigma n2.
Is there any physical significance of being able to split it into these two parts?
No, this is a subset of this. This is more general than this.
This is more.
Right. This is one set of states in which the overall state is represented as the product of state 1 and state 2, mode 1 and mode 2. If you do any measurements of any observable on mode 1, you don't touch mode 2. So measurements on mode 1 will not influence any of our observations of mode 2. If you detect, for example, whether there is a, suppose these were horizontal and vertical polarization states of two modes, okay, same frequency, same propagation direction. If I measure, if I pass this entire state through a polarizer which is horizontally oriented, corresponding to frequency omega 1, I split the omega 1 and omega 2, for example, then I will not influence any measurement of the second state. That does not happen in a state in which you cannot write it as the product state.
Not be an eigenvalue of that.
No, because what happens is any measurement done on one of the states influences the result of observation on the second state. And those are the entangled states where this kind of correlation exists between measurements performed on mode 1 and mode 2. And this is the most general. This is a specific type of the multimode state or two-mode state. Anything else? Okay. So before we look at beam splitter problem, I want to generalize this into a multimode state. So for example, suppose I take in classical picture a monochromatic wave. A monochromatic wave occupies time from t is equal to minus infinity to plus infinity, because it is exponential I omega t or cos omega t or sin omega t forever, for all times. The moment you make a finite duration wave, which means I say it is exponential I omega t or cos omega t from t is equal to 0 to capital T, it no more remains monochromatic, because you can take a Fourier transform and show that this contains many frequencies. So it's also, I can also build a wave which has a finite duration by adding waves of multiple frequencies, beating between various frequencies. So that becomes a non-monochromatic wave then. I cannot say I have a pulse which is monochromatic, because the moment you make a pulse of a finite duration, it is no more monochromatic, it has a finite spectral width. Now, the single mode state that we have looked at is a single frequency state, because single mode means single frequency, single polarization state, and one propagation direction, k vector. This is a state which exists for all times. If I take a single photon in that state, that single photon can be anywhere from t is equal to minus infinity to plus infinity. If I try to detect that photon, it may be anywhere, I don't know. Now I can form what are called as wave packets by superposing modes of different frequencies. So if I take, for example, if I take two frequencies, I will have beating between these two frequencies, and I will have a distribution which is not uniform right across time, but it will beat. So in the limit, what I can do is I can write a state a single photon state. What this implies is this is C1 11 02 03 plus C2 01 12 03 plus C3 01 02 13. How many photons are there in this state? So if I operate by the total number operator, so let me use some other index, m, am. Okay. So n psi this is equal to sigma m, sigma l, cl, am dagger am, 1l. I should be careful, I use different indices for the state and the number operator here. The total number operator consists of a sum of all the number operators corresponding to each mode. What is the value of this? If m is not equal to L, then the corresponding value of the number of photons in this is a short form, right? This is like this. So if m is equal to 2 and this is first one, it is 0 because there is 0, 2. So if m is not equal to L, this gives me 0. And if m is equal to L, this gives me 1L. So what this gives me is, so this is simply delta ml 1L. So what happens to this state? Sigma L if m is not equal to L, am dagger am is the number operator for the mth mode, and if this particular state corresponds to a value of L which is different from m, then there are no photons in that mth mode and in that state, and that is 0. Only m is equal to L terms will survive, and if m is equal to L, then am dagger al dagger al 1L is 1L. And so I get back Cl. So this means that this state is a single photon state. Total number of photons is 1. And you can show that this is not an eigenstate of am dagger am. That means, let me try to find out whether this is an eigenstate of the number operator of one of the states, one of the modes. So am dagger am dagger am of psi is equal to sigma L CL am dagger am 1L, which is how much? And this is not equal to psi. This is not an eigenstate. So what it means is, if you were to measure the number of photons in the mth mode, it's not defined. Every time you get a different value, you can calculate the expectation value. What will be the expectation value? Will be so mod Cm squared defines the probability of finding m photons in the state, in the that photon in the mth mode. That photon, there's only one photon, but that is in a superposition state. So these modes could be different frequencies. These modes could correspond in the summation. These modes in the summation could correspond to this same propagation direction, same polarization, but different frequencies. So by a choice of CL amplitudes, I can build a state where, just like in classical picture where I can have different frequencies adding up to give me a wave packet, I can build a single photon wave packet by choosing appropriate values of this coefficient CL. CL depends, if L represents various frequencies, because this L now corresponds to various frequencies, that is various modes correspond to various frequencies, all propagating in the same direction, having the same polarization state, then by an appropriate choice of CLs, mod CL square, I can add these up and it will become localized. It will become little more confined in time than in an infinite time space. Just like in classical, if I have a single frequency wave, that wave extends from minus infinity to plus infinity. But if I add multiple frequencies appropriately, in fact a continuous range of frequencies from omega 0 to omega 0 plus delta omega, I will get a wave packet whose duration will be 1 by delta omega. If the spectral width is delta omega, I will have a duration of the pulse which is 1 by delta omega, of the order of 1 by delta omega. So depending on the amplitude CL that I choose here, the combination I choose here, I can actually build a single photon wave packet. So it is this kind of wave packet that emerges when an atom is excited and emits spontaneously. Because when an atom is excited to an excited state and it emits by jumping down, it emits one photon. And that one photon is a wave packet like this, it's coming out. Its frequency is not well defined because the energy levels have a finite width, natural broadening, etc., etc. we discussed. So what is going to happen is, this photon which comes out is a single photon, but in a form like this. It's not in a single mode, it's in a superposition of modes. And as you will be able to measure, you can find the probability of detecting it after a certain time. Once you have excited the atom, you can put a detector here and find out what is the probability of detecting after 1 nanosecond, what is the probability after detecting the photon after 1.1 nanosecond, etc., etc., and you can form, and you will get a certain distribution with respect to time, which is exactly the spontaneous decay that you can measure in spontaneous emission process. So these are multimode single photon states, and when we say that we have a photon incident on a beam splitter or on a device, single photon incident, it is usually it's this kind of a wave packet that comes in. There's only one photon, but it is in a state in which it is a superposition of many modes, many frequencies. If you choose a larger spectrum of frequencies, you will have a narrower wave packet. If you choose a smaller spectrum of frequencies, you will have a larger wave packet, which means you can you have less uncertainty in where to find the photon within the wave packet if you have a narrower spectrum. And finally, when it becomes monochromatic, it's everywhere. So this is what is meant by in fact, generalization of a two-mode state into multimode state, and I can still have one photon in a multimode state, which means it is in a superposition state of many frequencies. If I take a photon propagating in one direction with one polarization state, it will be essentially, it is this concept, and so this state does not have a single frequency, it has many frequencies. As you can see here, the probability of detecting a photon in the mth mode, that means a particular frequency, is mod Cm square. And with an appropriate choice of mod Cm square, I can build a wave packet. Yes?
When I'm choosing a monochromatic field, that means there is large uncertainty in the time domain.
Yes. Yes.
That means I will not be able to detect where exactly I am detect the photon.
Yes. Yes. Which means if I were to, suppose I take a quasi-monochromatic single photon state. Quasi-monochromatic means it's almost monochromatic. So suppose it corresponds to a delta t of say 1 millisecond duration. So the corresponding frequency bit is 1 by 1 millisecond, which is 1 kilohertz or something like that, approximate, right? So 1 kilohertz bandwidth will give me 1 millisecond time. So I prepare a large number of identical 1 millisecond duration single photon states, and I do experiments on this, right? So what I will say is, within this 1 millisecond, you will not know when you will detect the photon. So I let this come on a detector. First detector may detect it right in the beginning, second detector may detect it after some time, third state. Please remember, one photon is detected only once. I am talking about multiple states, on an ensemble of systems. So this first one single photon state comes, I measure, I find a duration, within the 1 millisecond duration somewhere I will find it. The next one, I will find it another time.
So that means within this 1 millisecond duration, any detector can detect?
Will detect if this is precisely defined in this duration. Usually there is a wave packet which has a tail like this. So there is also a probability of detecting much later also, but the probability is very, very small. So this mod Cm square distribution will determine
which detector will detect in which time?
With proper probability. Suppose I could choose, suppose in the limit of the quantization volume, you see what is the frequency spacing between the various modes? It depends on the value of L that I have chosen when I quantize the electromagnetic field. If I were to increase L, the frequency spacing becomes smaller and smaller, and the frequencies become almost continuous. In that case, I can actually extend the sigma into an integral. Now, if I take mod Cm square as a function of frequency to be like a Gaussian function, that means there are various frequencies which are present with amplitude which depend on like a Gaussian function. The corresponding wave packet in the time domain will also be a Gaussian function, because the Fourier transform of a Gaussian is a Gaussian. So I will have a Gaussian single photon wave packet generated by a mod Cm square, which is again a Gaussian in frequency space. That means, so in that Gaussian, for example, I could have this is some value of m. So these are values of m which correspond to different values of frequencies. Each value of m corresponds to one particular frequency.
So we will have something like a discrete spectrum.
If L is finite, as L tends to infinite values, as I increase my quantization volume, these frequencies get closer and closer.
But then L over here refers to the different frequencies. I mean, every L refers to a frequency.
Yeah, in this summation,
Yes.
I am taking a combination of modes for which each L corresponds to different frequency, right?
Now, if we increase L, let it
Not this L, I am talking about capital L.
Oh.
The volume, the quantization volume, if I increase, the frequency spacing becomes smaller and smaller, and finally I will have all these frequencies. This continuous almost becomes. So there will be one particular value of m in this value, which will have its peak value, which corresponds to one particular frequency, and there will be different values of m where the frequencies, which corresponding frequencies where the amplitude will fall down. All it implies is the probability of detecting a photon with this frequency is largest within this wave packet. The probability of detecting a photon with this frequency is very, very small. This will lead in the time domain to a wave packet which exactly looks like a Gaussian, whose width will be inversely dependent on this width in the frequency space. The larger this width is, the smaller is the time width. The smaller this width is, the larger is the wave packet width in the time domain. So in a spontaneous emission, the exponential decay, we know. And the spectrum is, what is the Fourier transform of an exponentially decaying function? Lorentzian. So the spectrum that you will get is a Lorentzian spectrum, which also looks like a Gaussian. It's much broader. It's a Lorentzian spectrum, and the probability of detecting a photon at this instant will be maximum, and as the time delays, the probability will fall down to almost 0. And you will define a natural lifetime of the state, etc., etc. The lifetime of the state defines the spectral width of the emission. So they're all related through this. So this is a very interesting state because this is still a single photon state, but that photon is in a superposition of many frequencies. You can only define the probability of detecting a particular frequency for that photon.
Sir, with a different probability, I'll get different energy photon.
Yes, yes. Energy uncertain here because the frequencies are uncertain. If I have to precisely define the energy, it has to be a precise frequency. So there is uncertainty in the frequency, there is uncertainty in the energy, there is uncertainty in the position, when you will detect it, when it comes to you. In fact, I'll come to this detection a little later through another operator, but before that, so I thought I would introduce this, and this is a very interesting concept where I can generalize from a single mode state to a multimode state. In fact, I can further generalize to not having the same propagation direction or same polarization into this sum could represent different propagation directions and different frequencies, etc., etc. It's very general, okay? Okay. Now, what I want to do today is, because I want to introduce this beam splitter. This is a very important component in many experiments which deal with quantum aspects of light. I can build an interferometer with a beam splitter, I can do a lot of things, and beam splitter is also used as a model to incorporate losses or scattering, etc., in quantum optics discussions. So what is a beam splitter? I have a device in which light is incident from here, partially reflected and partly transmitted. Now, to simplify the mathematics, I am going to assume a beam splitter which is completely symmetric. That means the amplitude reflection of this wave is the same as the amplitude reflection of this wave on the other side. So this wave reflects this wave when it comes, when I am drawing double arrows here, is partly reflected and partly transmitted. So the single arrow gives you a single arrow reflected light, a single arrow transmitted light. A double arrow incident light gives me a double arrow reflected light and a double arrow transmitted light. And by symmetry, I am assuming that if this reflection coefficient is small r, this reflection coefficient is also small r. If this transmission coefficient is small t, this transmission coefficient is also small t. I can actually generalize to asymmetric situations, but we will restrict this. So let me call the amplitude reflection coefficient as small r and the amplitude transmission coefficient as small t. So let me call this the port 1, port 2, port 3 and port 4. There are 2 input ports and there are 2 output ports. It's a very general device actually. A lot of devices have 2 inputs and 2 outputs. Please note, even if you send light only in one port, the other port is still there. You may not be considering the second port, but there is a second port. And I will show you that in classical you can forget about the second port. In quantum, you cannot forget the second port because vacuum is incident from the second port all the time. Even if you don't send a light beam from here, there are modes, all modes are occupied all the time with vacuum at least. So, you cannot forget the fact that there is vacuum in this input incident, and that matters a lot in quantum mechanics, because if you neglect that, you have a problem in commutation relations. Okay. Now, so first let me do a classical analysis of this beam splitter and get some general relationships, and then we will quantize that through a particular procedure, and I'll tell you the procedure of getting the quantized relations between the annihilation operators of these fields 3 and 4 with respect to the fields 1 and 2. Okay, so if I have incident waves, let me call this E1, E2 are incident, E3 and E4 are the output ports. So what is E3? E3 will be R times E1 plus T times E2, and E4 will be T times E1 plus R times E2. If the R and T's were not the same, I have to write T prime and R prime for the second one. And please note, R and T are in general complex. These are amplitude reflection coefficients and amplitude transmission coefficients, not energy reflection coefficients. So these are complex. Now I need to satisfy energy conservation. So the sum of the energies in 3 and 4 must be equal to the sum of the energies in 1 and 2. If I have energy, certain energy incident from here, a certain energy incident from here, that must be either in 3 or 4. I am neglecting any absorption or any other scattering or anything else. So let me try to calculate. So the energy is proportional to intensity, which is proportional to the modulus square of the electric field. So let me calculate what is mod E3 square plus mod E4 square. So mod E3 square plus mod E4 square is equal to modulus of RE1 plus TE2 whole square plus modulus of TE1 plus RE2 whole square. This is equal to modulus R square modulus E1 square, and please note E1 and E2 could also be complex, they have phases, plus mod T square mod E2 square plus R T star E1 E2 star plus R star T E1 star E2 plus mod T square mod E1 square plus mod R square mod E2 square plus T R star E1 E2 star plus T star R E1 star E2. So let me collect the E1 square term. So this is mod E1 square into mod R square plus mod T square, this and this term, plus this and this gives me mod E2 square into mod R square plus mod T square plus E1 E2 star into R T star E1 E2 star E1 E2 star plus T R star plus E2 E1 star into R star T plus T star R. So this is the same as this is RT star plus TR star, RT star plus TR star. So this is actually mod E1 square mod R square plus mod T square plus mod E2 square mod R square plus mod T square plus RT star plus TR star into E1 E2 star plus E2 E1 star. Now what is the condition? mod E3 square plus mod E4 square must be equal to mod E1 square plus mod E2 square, irrespective of the values of E1 and E2. I can choose E1 is equal to 0, I can choose E2 is equal to 0, I can choose E1 is equal to E2, any combination I can choose, and still all the time I must have mod E3 square plus mod E4 square must be equal to mod E1 square plus mod E2 square. So what are the conditions I get? This must be equal to 1 and this must be 0. Otherwise, I cannot satisfy this equation for all values of any combination of U and E2. So I get, just simply by energy conservation, I get mod R square plus mod T square is equal to 1 and RT star plus R star T is equal to 0. So let me write R is equal to mod R exponential I phi R and T is equal to mod T exponential I phi T. So this is mod R into mod T into exponential I phi R minus phi T plus exponential minus I phi R minus phi T R T star plus R star T. So mod R and mod T are not 0, need not be 0. So this tells me cosine of so this means phi R minus phi T must be equal to this is a symmetric situation. If you do not have a symmetric situation, you will get a different combination of phases of R, R prime, T, T prime, etc. You have another equation there. But here I get, and this is very general, I have not assumed anything. This is actually a general 4-port device. 2 input port, 2 output ports. The phases of the reflected and the transmitted components must be different by pi by 2 if it is a symmetric device. So, for example, if my beam splitter was a 3D 50% beam splitter, which means it reflects 50% of the light and transmits 50% of the light. So, what I can do is I choose, for example, phi t is equal to 0 and phi r is equal to pi by 2. So as to satisfy this condition. So, t is real and r is imaginary. Phi r is pi by 2. So, if I have a 50% beam splitter, I have r is equal to, what is the magnitude of r? 1 by root 2, and there is an exponential I phi r, so this is I by root 2, and t is equal to, this is for a 50% beam splitter. The phase difference is independent of whether you are choosing 50% beam splitter or 80% beam splitter. It's always pi by 2 in this symmetric situation. So, if I go back and write the earlier equations, I find E3 is equal to I by root 2 E1 plus 1 by root 2 E2, and E4 is equal to 1 by root 2 E1 plus I by root 2 E2.
Can't we do phi t equal to 0 and phi r equal to pi by 2 for all, even if we have a 25%?
Yeah. But symmetric. What I am saying is, I have assumed R is equal to R prime and T equal to T prime. If you do not have symmetry, for example, if I have a glass air interface, at the interface is not symmetric situation. So the reflection coefficient from here and transmission coefficient complex, I am talking about complex reflection and transmission coefficients could be different, so I have to work it out, and it's very simple. It's just the same analysis, except that I need to ensure that when I write this equation, I write R and T prime and R prime here, that's all. And I do the same analysis, and you can find out the relationship between the phases of the various coefficients. So in fact, this is in the matrix form, E3, E4 is equal to I by root 2, 1 by root 2, 1 by root 2 and I by root 2. Okay, so these are classical relations. There is no quantum mechanics in this. These are completely classical equations. Now, use the following procedure to understand the property of the beam splitter in the quantum terms. So these electric fields now become operators, and I will, for example, I have a relationship between the annihilation operators of the mode coming out at 3 and the modes 1 and 2. Similarly, the annihilation operators for 4 and 1 and 3, 2. So by quantization, I would say that the annihilation operator A3 corresponding to the field coming out in the port 3 is actually I by root 2 A1 plus 1 by root 2 A2, and A4 is 1 by root 2 A1 plus I by root 2 A2. A quantum mechanical operation of the beam splitter is written in terms of the annihilation operators of the fields coming out in 3 and 4 port, their relationship to the annihilation operators of the fields coming in 1 and 2.
Why is it the same?
I'm just using I'm sort of proposing here that I will quantize this by this operation, and I will show you that A3 and A4 satisfy the commutation relations that are required for A3 and A4. A3 must satisfy A3 dagger must be 1 and A4 dagger must be 1. That is also satisfied from this equation. So actually what I am trying to do is I am just replacing, which I expect it to be all right, replacing the classical electric field operators by quantum electric field operators. Classical electric fields by quantum electric field operators. And the electric fields are replaced by operators.
Commutation relation might be satisfied with some other combination. For A3 and A4.
No, this is the quantum equivalent of this beam splitter, which has this classical relationships.
How do we come to that expression?
Which expression? This expression I have got from classical.
A3 and A4.
This is classical. I replace the electric fields by the corresponding electric field operators.
I can see that, but
yeah.
Why are we doing exactly that?
Actually, I must, in a completely correct picture, I must represent the beam splitter by a unitary operator and work out its effect on the input wave function or the input get state that is coming in. That's much more complex. A complex analysis has to be done. But this gives me the same result. I'm not showing you, I'm not proving that this is right, but I'm actually expanding this classical equations into corresponding quantum equations, and this quantum equations will predict the results of all measurement that I do with this beam splitter, for example. This is where I have actually gone from a classical picture of beam splitter to a quantum picture of beam splitter.
But if we in that expression for E3 and E4 that we tried classically, if we replace the quantum operators, the operators for E3 and E4.
No, assume that this is a like a postulate. I have actually postulated here in this here, but normally I would have to understand the quantum mechanical operation of the beam splitter by taking it as an operator operating on the input get states, etc., etc. That's much more complex, but this is the procedure which I employ, and I find everything is consistent. For example, I'll tell you, suppose I had not taken the second port into account, and I had said that let me look at the following problem. I have a wave incident on a beam splitter. E1 is incident, generates E2 and E3 and E4. I would have got E3 is equal to RE1, right? So I would have replaced this by now if I calculate the commutation relation A3 dagger is equal to R A1 R star A1 dagger, which is equal to mod R square A1 A1 dagger equal to mod R square. That's not 1. It's not a correct relationship. So this is why I said I cannot neglect this port.
I think just writing, even if we replace the electric field by the electric field operator in quantum mechanics, we still have A dagger into E bar R chi, where chi will have a different k vector for all the 4 ports. So it's not intuitive to just directly, replace it by the annihilation operator and write it. If I replace the electric field by the operator, exact operator that we derived,
Yes, yes.
then it's not intuitive still to write the previous expression that we wrote.
No, what I am trying to say is, I am giving you a procedure. Let me assume that I am giving you a procedure to get the quantum equations of the beam splitter from the classical equations. This is done in many other areas where I get the classical equations and I replace the variables by corresponding quantum mechanical operators, and I get a relationship. And of course, the final thing is whether this is correct or not will be predicted by whether these equations predict correct experimental observations. There must be surely more complicated procedures of getting these equations from by analyzing the beam splitter as a quantum mechanical operator, etc., etc. But I think it's much more complicated. And finally, it seems the result is this is the right result. So let me assume that this is the corresponding operator equations representing, connecting the operators of the transmitted and reflected fields to the operators in the input fields 1 and 2 and the input 1 and 2. In fact, I will do a similar thing when I come to parametric down conversion. Remember, in parametric down conversion, we had obtained an equation relating the electric field at the output with the electric fields at the input of the signal and idler. I can go into the quantum mechanical picture by replacing those electric fields by annihilation or creation operator. And I will show you that is the equation that I get there is the equation for squeezing. Although this is not a very rigorous procedure, I am not following a rigorous procedure of deriving these equations, but because of these classical equations, I am sort of applying a procedure, I should say, which seems to be correct, that I replace these electric field operators by the corresponding annihilation of electric fields by the corresponding annihilation operators, and get a relationship between the annihilation operators in ports 3 and 4 with respect to ports 1 and 2. Now you can check, for example, here A3 dagger is I by root 2 A1 plus 1 by root 2 A2 minus I by root 2 A1 dagger plus 1 by root 2 A2 dagger. So this is equal to half A1 dagger plus I by 2 A1 A2 dagger minus I by 2 A2 A1 dagger plus half A2 dagger. Now please note, inputs 1 and 2 are completely independent of each other. So the annihilation operators A1 and A2 commute. This is 0, this is 0. This is equal to 1, this is equal to 1, and I get A3 dagger equal to 1. Similarly, you can show A4 dagger is 1. So if I neglected the second port at the input, as I showed you, I am not able to satisfy the commutation relation at the output annihilation operator, and that's not a correct transformation. Okay. So let me look at one example of this operator equations, and that is an example where I assume a single photon is incident on a beam splitter from port 1. Okay, so this is a 1 photon state and here it is vacuum. So I want to find out what comes out of this beam splitter. So input side 1 1, which is actually and this is actually A1 dagger because 1 1 is A1 dagger 0 1. Now, as far as the states are concerned, I know that if there was vacuum incident in 1 and vacuum incident in 2, I will get vacuum coming out of 3 and vacuum coming out of 4. So, this beam splitter transforms this state to an output which is both vacuum, and the beam splitter transforms A1 in terms of A3 and A4. So, I have to invert these equations and calculate A1 in terms of A3 and A4. So, if I multiply this, and I can show that A1 is equal to, so I get A1 here I multiply this by I invert this equation. So, let me give you the inverted equation here, minus I by root 2 A3 plus 1 by root 2 A4. And similarly find out A2 from here in terms of A3 and A4. So, A1 depends on A3 and A4, and so if this is the input state, 0102 goes to 0304, A1 dagger gets replaced by 3 and 4 operators, and the output state becomes minus I by root 2 A3, no, so it's a dagger, so plus I by root 2 A3 dagger plus 1 by root 2 A4 dagger operating on 0304. So, I have replaced A1 dagger by the corresponding operators in terms of A3 and A4, and I have replaced the 0102 state by 0304 state. So, what is this? This is I by root 2, A3 dagger on this, 1304 plus 1 by root 2, A4 dagger on this gives me A3 dagger operates on 03 gives me 13, A4 dagger operates on 04 to give me 14. What is this state? This is a superposition state which we had discussed earlier. What it implies is the output state is a superposition of the photon being present in port 3. So, if I have a single photon coming from here, you generate a superposition state of 3 and 4, where the photon could be either here or here. Actually, it is both, with probability is half because of this 1 by root 2 amplitudes here. The probability of detecting 1304 is which is 1 by 2. And similarly, the probability of detecting 0314 is also half. So, the single photon now goes into a superposition state of being in this part of the beam splitter and in this part of the beam splitter. It will continue to remain in this superposition state unless it is disturbed. And please note that I can go on for a million miles and still be in the superposition state of both arms. And if you were to put a detector on one of the arms, you will suddenly detect it or not detect it. Now, I am looking at a wave packet. See, this is a single photon state, but single photons can be in a wave packet now. Okay, so it's as if Problem is, it is as if the photon is in a superposition state in both arms, but suddenly collapses. This is a problem in quantum mechanics. There is a collapse of the wave function. A measurement collapses the wave function, and that collapse has no space variable in this picture. So it is not that the beam splitter is either reflecting or transmitting the photon. It is reflecting and transmitting. It is in both arms. In fact, what I will do in the next class is to build a Mach-Zehnder interferometer from here. And what you will find is that there is interference effect. So single photon enters the beam split, the Mach-Zehnder interferometer, and interferes with itself. The probability amplitudes actually are interfering. It is not that the part of the particle is going here, part of the particle is going here. The probability amplitudes of both the arms are interfering to produce a probability of being detected at the output in either of the arms. Okay, I think we'll stop here. Any questions? Okay, thank you.